Hi, my name is Christina Dimarino. In this video, I'll talk about the design, fabrication, and testing of 50 kilowatt, 3-phase AC to DC bidirectional converter for 200 degree C ambient operation. The application background for this project is for a more electric aircraft, or MEA. In more electric aircrafts, they are desired to embed the starter generator in the engine compartment such that the bulky mechanical gearboxes can be eliminated. This results in improved fuel savings and reliability and reduces maintenance costs. However, there are several challenges associated with embedding the starter generator in the engine, including exposing the electronics to the harsh engine environment, which can reach temperatures up to 200 or 250 degrees Celsius. Consequently, this work aims to demonstrate a fully high-temperature, high-power density 50 kilowatt converter with 70 degree C liquid cooling, plus minus 270 volt DC rating, 70 kilohertz switching frequency. These converters can be interleaved to achieve the full 150 kilowatt power rating. At the time of this project, no high-temperature power modules were commercially available. Therefore, part of this project involved the design and fabrication of power modules rated for 200 degree C operation. This is a look at the 200 degree C 1.2 kV 120 amp silicon carbide half-bridge power module that was fabricated in our CPES packaging lab. 1.2 kV silicon carbide MOSFETs and Schottky diodes were used in this power module due to their high temperature and high speed capabilities. High lead solder was used for the die attach. In the back, we have the laminated DC bus bar, which uses Nomex for high temperature insulation. And on the other side, we have the AC power terminal. High-temperature ceramic capacitors are embedded inside the module for decoupling from the bus bar parasitics. The module also includes an embedded NTC thermistor for sensing of the substrate temperature. Aluminum nitride was selected as the substrate material due to its high thermal conductivity and close CTE match to silicon carbide. SiC was chosen as the base plate material due to its low CTE, lightweight, and reasonable cost. The substrate is bonded to the base plate using epoxy adhesive. The housing is made of Torolan, a high-temperature plastic, and is secured to the base plate with silver epoxy. This is a schematic of the 50 kilowatt converter, where the components inside the dash red box are to be operated in the high-temperature environment. As was mentioned earlier, custom high-temperature silicon carbide power modules were fabricated in the CPES packaging lab due to the lack of commercially available high-temperature modules at the start of this project. An extensive survey was conducted on high-temperature magnetics in order to realize a high-temperature EMI filter. A survey on high-temperature capacitors was also performed. Through this survey, it was determined that multi-layer ceramic chip capacitors were the best choice for this application due to their capacitance and voltage ratings and reasonable high-temperature performance. These capacitors were characterized in order to evaluate their high-temperature performance. High-temperature laminated DC bus bar was fabricated using Nomex dielectric material for the high-temperature insulation. High-temperature sensors were purchased from vendors such as Honeywell. A high-temperature gate drive from SiC was used to drive the high-temperature power modules. For this work, it was assumed that TI's high-temperature controller could be used. Here's a look at the system arrangement. On the left, we have the signal input to the control board, where the sensors are mounted. The SiC gate drivers are located underneath the control board, and gate resistor boards are used to interface to the silicon carbide power modules. The modules are on a cold plate which has 70 degree C liquid cooling. The laminated DC bus bar is shown on the right, where it can be seen that the DC link capacitors are mounted to the underside of the bus bar and rest on top of the cold plate. This is the assembled high-temperature 50 kilowatt AC to DC bidirectional 3-phase converter, with the motherboard removed and the lid partially cut. In this way, you can see the high-temperature gate drive from SiC connect to the high-temperature power module through a gate resistor board. The power module is then connected to a laminated high-temperature DC bus bar with the DC link capacitors mechanically connected underneath. The ceramic capacitors and the power modules are on top of a 70° C liquid-cooled cold plate. This converter was put into a thermal chamber where the ambient temperature was set to 200° Celsius. The module substrate temperatures were monitored using the embedded NTC thermistors, and additional thermocouples were used to sense the ambient and cold plate temperatures. The converter was immersed in this high-temperature environment for 1.5 hours while electrical tests were performed. Based on the thermistor measurements, the module substrate temperatures were at approximately 100° Celsius. Double pulse tests were then performed at 540 volts and 115 amps. The turn-on and turn-off waveforms from the double pulse tests are shown here, where the yellow waveform is the gate source voltage, the blue waveform is the drain source voltage, and the green is the inductor current. The ringing shown in these waveforms is from the measurements and is not actually seen on the modules. Due to the lack of high-temperature voltage probes, long high-temperature wire was extended from the power modules to outside the thermal chamber. Testing at room temperature verified that this ringing is due to the added parasitics and noise from the long twisted wires and is not seen on the modules. In conclusion, a fully high-temperature 50 kilowatt converter was designed, fabricated, and tested. The converter showed good high-temperature performance in a 200° C ambient environment, even after soaking for more than 1.5 hours. This work thus demonstrated the feasibility of a high-temperature converter, which could be used in applications such as embedded generators in more electric aircrafts. Thank you very much for watching this video.